Oh, hi. Up on this board, I've gone ahead and compartmentalized some compounds. What we have on the far left are the inert gases, the group 8 or 18s, such as helium, neon, argon. You can look at a periodic table and see that these are the inert gases. I've got molecules listed, which are a combination of non-metals only, and broken it up into Roman numeral 1, 2, and 3. Ionic compounds, which are a combination of metal and non-metal, and totally think of these things as being solids, where what's keeping them together are charges. So we have oppositely charged magnets. Over on the right side, completely new topic for us called network covalent compounds. There are not many of these known, and I would consider these to be the most common three: graphite, diamonds, and quartz. Make a couple of notes here. Graphite is 100% pure carbon. So let me write down pure carbon. And graphite appears as sheets. Let me hold up a model. And this is going to be a sideways model of graphite. Now ignore these little metal rods because they're not supposed to be there. They're part of the model itself. These are not to be taken as bonds. What we have is, if I go ahead and turn it this way, we have hexagon, 6-membered carbon rings. And these rings are all fused together. Now I'm going to just take a piece of common plastic here and hold it up this way, saying, please go ahead and envision that this top layer is a sheet. It goes on for a long ways in 2 dimensions. Now here's another sheet. And they're not bonded together. This sheet and the top sheet are not bonded together. Those are just pillars keeping the model together. There's very little attraction between this sheet and the middle one. And then one more here. Now graphite doesn't exist as 3 sheets. It exists as a bunch of sheets. But let me take 3 of these common plastic sheets and tell you to think of them as being sheets of carbon graphite. The sheets are very, very slick over one another. Very nice model because there's very little interaction between this sheet and this sheet. Carbon graphite makes for a nice lubricant. Locksmiths have it as a crushed black powder, and they'll squeeze it out of a tube into a lock so your key slides in nice and easy. If you take carbon graphite and crush it, kind of press it down into a rod, you can insert it into a tube of wood, make yourself a pencil. If you take carbon graphite and crunch it into like a block, you can have a charcoal briquette. If you take it and put a little bit of a starter in there, what I have over here is I've got rifle powder. Rifle powder, or known as gunpowder, and this is one really old can that we found at a garage sale. This is probably like a surplus from World War II that's been boxed up and sold to people. Tiny little black pellets of carbon graphite and a starter. That starter gets things going. So this isn't like a barbecue where I have to start it with paper or bring in an exterior fluid. There's a little bit of starter on here, and it's giving off a nice amount of heat. The reason it works as like a projectile launcher is because envision this like in a cannon, pressure building up and then shooting a projectile. So we've got carbon graphite. It's known as a network covalent compound because it's a network. It's not one atom, it's not 60 atoms, it's not 100 atoms, it's a whole bunch, thousands, trillions, trillions, trillions of atoms. Now this has a very high melting point. So already on this chart, let me go ahead and say things over to the right, these network covalent compounds, the clear winners, these are going to have very high melting points. Now in order to melt graphite, you need to put in a tremendous amount of heat. I'm not going to list the temperature, but tell you it's in the range of about 4,000 centigrade. Temperature of the outside of the sun, just incredible heat. And the reason it's so high is because in order to melt, you need to loosen these carbon atoms. You need them to flow over one another, make a melt. And in order to loosen them all up, imagine all these bonds, the energy there that you need to overcome. So you have to put in a tremendous amount of heat to get all of those bonds. That's not true with something, say, of an inert gas. Inert gases just exist as points in space with very little interaction. These have a tremendous amount of interaction. Next down the list is diamond. And diamond, oh, diamond, girl's best friend, hardest substance, naturally occurring, all these little old-time sayings. We have a box of fake diamonds here. Diamonds are clear, 100% pure carbon, and the deal on diamonds is that we have sp3 hybridized carbons. We have one carbon surrounded by 4 neighbors, and that goes on and on and on. So it's a nice model, but it's not very good in the sense that it's small. It's supposed to be like miles long, showing you trillions upon trillions upon trillions of carbon atoms. And again, why is it hard? Why does it melt at a high temperature? It's because in order to like break it or interrupt these interactions, you have to put in a tremendous amount of energy. So there we have it. Pure carbon, graphite, pure carbon, diamond. Let me write pure carbon next to diamond, but also point out the third one is quartz. So next to diamonds, pure carbon as well. And people have said things like, well, graphite is stable, and what the Earth has done over years is heated it up and pressurized it into this configuration, diamonds. Quartz is not pure carbon, but it is a network covalent compound. Quartz is made of SiO2 units. One could say that it's similar in structure to diamond, in that what we have is we have silicon surrounded by 4 oxygens. They're not flat as in the board. They make more or less like pyramids, where we have 3 oxygens down below and 1 oxygen on top. So go ahead and sneak a silicon in the middle there, and you can show the 4 bonds if you'd like, and we have these triangle-based pyramids. Now these don't stop going, okay, this is all we have, because it doesn't even match the formula, SiO2, Si, there's 4 oxygens, but instead what's happening is we have these neighbors, and it goes on in 3 dimensions. So let's explain the name. Network, because we have a 3-dimensional, or in the case of graphite, 2-dimensional, but the idea is ongoing structure. Covalent, because it turns out these are made out of non-metals. So we don't have positive and negative charges, we have covalent or sharing of electron bonds. These melt at extremely high temperature, call it 4,000 centigrade.